Welcome to Risk Engineers Talk Governance. In this episode, due diligence engineers Richard Robinson and Gaye Francis discuss the risk curve and modelling the ideal hazard. We hope you enjoy the chat. If you do, please support our work by giving us a rating and subscribing on your favourite podcast platform. And if you'd like more information on R2A, our newsletter and resources, or have any feedback or topic ideas, please head to the website r2a.com.au.
Hi Richard, welcome to another podcast session.
Good morning, Gaye.
Morning. Today we're going to talk about modelling the ideal hazard, if that really exists.
As we mentioned earlier, small children can be in this category.
Ideal hazards, maybe. So what we're going to do, just as a introduction, I guess, we're going to use some slides in this particular podcast. So if you usually just listen to us, and it might be worth transferring over to the YouTube channel, but we will explain the slides as best we can as we're holding them up as well. So not critical to go to the YouTube channel, but just be aware that we will be holding some slides up.
Now, the reason why we're doing this particular podcast, because it's come to our attention that a lot of people have decided to use heat maps again with regards to downside risk.
For decision-making purposes.
Rather than just reporting purposes. And we've talked about this in the past, but I thought it was worth just mathematically explaining a little more robustly why using it as a decision-making tool will put you in the wrong place. Now, the way I'll put up the slide here, but normally R2A deals with sort of three core areas of risk. Downside risk, the risk from which there's no prospect of gain. That's safety risk, which is all negative.
Yep. And that's your graph on your left-hand side.
Upside downside risk, which is what popped up in the 80s, particularly with the commercial people. So you can buy shares in the stock market, the price can go up or the price can go down. Or downside risk from a promised upside risk position, which is what project risk is about. Those three things are actually quite different for a start. But today we're just talking about downside safety risk in the first instance. Now, if you just look at that slide, it is downside. It's going negative, right? But when you're actually doing this sort of stuff, most people use the heat map. They've got the heat map on the positive side of things, which is sort of, at one level, a little bit peculiar.
So when Richard says the heat map, it's typically the 5x5 matrix like we see in the Australian Standard and things like that.
Red, amber, green sort of thing. We're green's low risk and reds usually don't go there. Now, one of the interesting things about these things, they're normally done on a log-log scale. And the reason why that's the case, there's actually some technical competent reasons for that, is that back in the 30s, a fellow called Heinrich in the US was doing studies of all US accidents, and that was built upon by a guy called Bird. And you probably read about it, the accident triangle, where one very serious incident was accompanied by 10 not so serious events, and then about 30 or 40 or 50 other events. And by the time you get down to the near misses, you're sort of in the hundreds, close to 1,000, that sort of thing. The numbers are always a bit flaky because how many people actually report near misses when it comes to the crunch?
Yes.
But the general recognition was, and I've never seen anybody disagree with this, is that generally a tenfold increase in consequence is accompanied by a tenfold decrease in risk. And that's a hyperbolic curve.
Yep.
Y equals 1 on X, okay?
Thanks for a maths lesson, Richard.
Oh, we haven't got there yet, Gaye. Now, what people do on a heat map ordinarily is they just spot the dot, 1 point. And if you assume the risk follows a line of constant risk, so that's on a log-log scale, that will be a 45-degree slope, which is the way most people normally sort of treat these things.
Yeah.
And a tenfold increase in consequence accompanied by a tenfold decrease in likelihood. Then if you pick 1 point in that line, at one level you have characterised the full possible range of outcomes of that risk. Because a very small one happens a lot, and a very rare one, a very big one, is very rare.
Yep.
The problem, of course, is that no hazard has a line of constant risk associated with it. Every hazard has its own unique risk curve associated with it.
And it's often wobbly.
Yeah, well, pretty wobbling. I mean, I've sort of prepared a prior document.
A non-ideal.
A non-ideal. And what that's basically showing is that, there's probably a wobbles. I mean, if you just think about a high voltage hazard or something like that, if the arc flashes, it's either pretty much going to hit you or it's going to miss you.
Yeah.
Or if there's two of you walking along,
one goes and one doesn't.
Or maybe both of you go. But it'll have jumps and bumps in it. But nevertheless, if you were actually trying to work out the actual risk associated with this thing, what you really need to know is the area under the risk curve.
Okay.
And that means you've got to really integrate the area under the risk curve. Now, if you take the ideal risk curve, which is y
Your
equals
slope.
1 on x,
Yeah.
which is the hyperbolic, and then you plot that on an ordinary graph paper, it looks something like that, which is, well, if you think of a hyperbolic risk curve, it's obviously a tenfold increase. Well, you get a shape like that. Now, in practical terms, this always made a lot of sense to me, because if you want to stay away from the high the one place you do not want to be is high consequence, high likelihood.
Correct.
And that means you're in the top left-hand corner of this diagram, the bright spot, the hot spot on the chart. And if you stay equidistant away from a point up there, what shape curve must you get?
Hyperbolic.
This is really getting good, Gaye.
It is.
Yeah, and if you want to integrate the area of the risk curve, and it's a function y equals 1 over x, Gaye, what's the integral of 1 over x? It's the natural log.
It's a natural log. There you go.
Now, if you start integrating the natural log, one of the difficulties you have with a hyperbola is it goes asymptotic in both directions. So if you integrate from 0 to infinity,
Yeah.
you get an infinite number, which makes it mathematically very inconvenient.
Almost impossible, you would think.
So therefore you have to integrate over range. Now, obviously, if it's such a small matter, then you don't worry about the really small events, because nobody's being hurt, and maybe somebody gets a bruise, something like that, but
Yeah.
it happens an awful lot, but who cares?
Right.
It's like a bit like stubbing your toe in the morning when you get up.
It is.
It's very
It
annoying,
hurts.
but you still go to work.
That's true.
Now, and then obviously you've got to put a limit on the other end, because if you keep saying, planet-destroying meteorites constitute a hazard that we have to deal with,
Yes.
then
What's
it's
a
it's a 1 by
realistic-
10 to the minus 12 and on minus 14. How far do you integrate the other direction?
Mm-hmm.
So you have to integrate under the line over region.
Yeah.
And what
How do you select
change
that
does it get?
region?
Now, the plot that I just put up was just basically 1 over x. I just put, so it's going through the 1 over the one point, i.e. So therefore, if you just sort of start integrating from, say, 1 to 10, 1 to 100, 1 to 1,000, 1 to 10,000, something like that,
Yeah.
what's the actual increase you get over the actual line, which is, at that point is just 1? It's a line of constant risk going through 1, right?
Yeah.
And the answer is quite significant. The handy thing about integrating that particular line is that you have to, the integral is, the upper limit, sub ln of the upper limit minus ln of the lower limit. If the lower limit happens to be 1, that makes the natural log 0.
Okay.
So, or if anybody's interested in this sort of stuff and you want to do it yourself, that's easy. But just to give you the rough idea, if you integrate from 1 to 10
Yes.
of 1 over x,
Yeah.
and the natural log, it goes up by a factor of 2 point something. If you integrate from 1 to 100, it goes up by a factor of 4.6. From 1 to 1,000, it goes up 6.9. From 1 to 100,000, it goes up to 11 times the value of risk. And if you went to 1 in a million, it goes up by a factor of something like 13, an order of magnitude. That's significant, particularly when you're dealing with high consequence, low likelihood events that happen very rarely.
Yeah.
And as I pointed out to you before we started this podcast, if you want to be statistically significant about failures, you've got to fail at least 3 times doing the same thing, which from a risk point of view is not a particularly good thing to do.
No. And I don't think that's particularly a lot of times to have to fail either.
No, what's the line? If at first you don't succeed, try again.
So there's
Well,
your
then it's
3, as you
statistically
said.
significant, which must be useful. I don't know. Now, the point about all this is everybody spots the dot and thinks, I don't know what they sometimes think. I think they think they've done a risk assessment.
Yeah.
But what you've done is a fearfully complicated thing. And you want to be clear, we've only at this point considering downside, pure risk, safety risk. We're not talking about upside, normal distribution risk that the commercial people like doing. That's why people do PhDs in these things. And we certainly haven't been considering downside risk from the point of view of a critical project. Because remember, with the project, there's downside risk from the promised upside risk position.
So where do you start your curve?
Well, remember, the whole point of our project due diligence process is you start off with the critical things because you cannot let a showstopper happen. It's not possible with a big project.
But that means we're still, I think what this is saying is typically you know what the potential range of consequences are. characterising the likelihood associated with the consequences is always the difficult part.
And if you're talking about high consequence, high likelihood, like for example, a explosive fuel mixture in the chamber, and you just spot the dot and say 1 in a million is here, you have probably underestimated it by an order of magnitude.
And I think that's, well, primarily that was one of the reasons why the WHS legislation came in, and the due diligence approach was to eliminate all of those games that people played with the likelihood things, with the likelihood arguments.
And what have the Kiwis done with their new amendment bill?
Yeah,
They're changing their legislation to say that you must focus on the critical ones first.
Critical ones, but you're also still focusing on the controls that you can put in place. So there's no discussion around, you're only testing the likelihood element when you're looking at the control that you can put in place as a balance argument.
It's a reasonableness test.
And I think what we've seen in a lot of these sort of stuff, when people are using the risk characterisation 5x5 matrix and characterising risk, they get bogged down in the detail, because it's always an argument about what the risk is before you even start to look at the controls you can put in place.
But the other problem they've got is the scope of their risk curve. I mean, if you're talking about a 1 in a million event, an awful lot of people say that 99.9, 0.001, rare is 1 in 1,000. No.
Yeah. And I think that's
they don't just cover the range.
No. And we've found that when we have been doing some of these, the risk matrix curves risk matrices are really good at the communication aspect, and we've done it for enterprise risk frameworks and things like that. So you're characterising you're communicating things and characterising things in the system of
the value system of the decision makers.
But often you're right, the 5x5 scale is not big enough to characterise all of the issues of a water company, for example, because they're dealing with dam failures, but they're dealing with burst pipes as well.
Same thing with hospitals, but any large organisation, the state governments, remember we did a couple of jobs for hospitals. You've got the hospital, what's critical for an individual hospital isn't necessarily critical for the Department of Health, and what's critical for the Department of Health isn't necessarily critical for the state as a whole. So that's another 2 orders of magnitude, and BHP, Billiton used to do it that way too.
So I think we're not saying don't use any of these things, but what we're saying is understand what they can be used for, their limitations, and have that understanding when you're doing it. But safety risk is still asking you to say, what are all the credible critical issues? What are the controls you can put in place, and what is reasonable in the circumstances?
And that's where the Kiwis are going. I hope the Australians catch up quickly.
Here's hoping, but as you said, New Zealand's definitely leading the way. That was a very technical podcast for us. And
For some.
For some, yes. Other people enjoy this sort of stuff, I understand. But thanks, Richard, for explaining that, and we will see you next time.
Thanks, Gaye.